In 2.2 we look at simplifying radical expressions. So quick review of terminology. In the first figure here we have C representing the coefficient, N is the index, and R is the radicand. So in the expression on the right, 2 times the cube root of 5, 2 is the coefficient. And it's just like when you multiply a number by a variable 2x, you would say 2 was the coefficient. 3 is the index, and 5 is the radicand in this case. Now, also recall that if the index is 2, we don't normally write it in. So 2 root 5, you wouldn't write in the index of 2, but it is there really. And again, review of multiplying. When you multiply radicals, it's really quite straightforward. You just have to multiply the two radicands, but only if the indices are the same. So if you have the square root of a times the square root of b, that is the square root of the product of ab. Similarly, if it were the cube root of a times the cube root of b, that would be the cube root of the product of a and b. But you cannot simplify in any meaningful way the square root of a times the cube root of b. It doesn't work. Okay, so let's take a look at comparing and ordering. So let's say we have these three radicals. If you wanted to put them into correct order by size, by magnitude, it's pretty difficult to tell without plugging them into a calculator and getting a decimal approximation. But if the radicands, or rather if the indices are all the same, you can turn them all into entire radicals and compare them quite easily. So 2 root 7 you can write as root 4 times root 7. So we've replaced the 2 with root 4. And then just follow the rules of multiplying and you get root 28. We can do the same thing with 3 root 3. We want to replace 3 with a root, so 3 is the same as root 9. And root 9 times root 3 gives you root 27. So you can see that 2 root 7 is just slightly bigger than 3 root 3. 4 root 2, we can replace that with root 16 times root 2, and that becomes root 32. So root 32 is the largest of those three, so therefore 4 root 2 is the largest of those three, and the smallest would be 3 root 3. What if the indices are different? So what if you have 3 root 15 and you want to compare that to root 6? When the indices are different, there's really nothing you can do here except for reach for the calculator and figure out the decimal approximations of these and try and figure out which one's bigger based on the decimal approximation. There's really no shortcut. Alright, multiplying and dividing. Alright, we've seen multiplying, so what about dividing? So dividing radicals is similarly easy. If you have the nth root of a and you divide that by the nth root of b, you can write that as the nth root of a over b. And we can use this rule going both ways. In other words, if our radicand is a fraction, a over b, we can split it apart and write it as the nth root of a over the nth root of b. Now, once again, the radicands, or rather the indices, have to be the same. If we had the square root of a over the cube root of b, we can't combine those really in any meaningful way. So let's see this in action. So what if we wanted to write the following as an entire radical? Let's say we have 3 times the square root of 4 over 3. Well, we would take 3, replace it with root 9, and you have root 9 times root 4 over 3. You can multiply the two radicands because the indices are the same. So you end up with the square root of 9 times 4 over 3. And when you're multiplying an integer by a fraction like this, you always want to see if you can simplify first. Instead of just multiplying the 9 and the 4 to get 36 over 3, always make your life a bit easier by doing the 9 divided by 3 first. That gives you 3. 3 times 4 is 12. So this is just root 12. Now, what if we just had root 4 over 3 on its own? If we just had root 4 over 3, this textbook that you're using presents sort of final answers or simplified answers with non-integer radicands, but in some contexts and some textbooks present only integer radicands as being fully simplified. So what if you're in a situation where you need or want only only radicands that are integers, and you don't accept 4 over 3 as a simplified radicand? Well, here's where you would follow the rule we just saw for dividing, except you'd be breaking this apart into root 4 over root 3. Now, root 4 is straightforward enough. That is just 2. And so you'd have 2 over root 3. Now, again, here we're presented with a different problem, and that is that, again, in some contexts, it's fine to have a radicand or a radical in the denominator. And in fact, in trigonometry, especially next year in Math 12, you will use lots of expressions with the radicand, the radical in the denominator. But again, in some contexts, it's not considered simplified if you have a radical in the denominator. So how do you get rid of that root 3 in the denominator? You do something called rationalizing the denominator. And to do that with a simple denominator like root 3 is pretty straightforward. You just simply multiply both the denominator and the numerator by root 3. And since you're multiplying root 3 by itself, you're squaring it, leaving you with the integer 3. And the numerator just becomes 2 root 3. So that would be considered sort of fully simplified under all circumstances, because the radicand is an integer and the denominator is rational. But the rules are nowhere near as strict here. Different contexts you will allow for non-integer radicands, and different contexts you will allow for denominators that are radicals as well. Okay, so let's move on. What if you want to write as a mixed radical? So let's say you have the cube root of negative 48 over 135. So the key to doing this is looking at the numerator and the denominator and trying to find perfect cube factors. All right, because we're taking the cube roots of these things, if we can find a perfect cube factor, then we can simplify that as an integer. And we can attach the negative sign either to the numerator or the denominator. It doesn't really matter. If we attach it to the numerator, we can take out a perfect cube factor of negative 8. Remember, a negative is also a perfect cube. So here we can write this as the cube root of negative 8 times the cube root of 6. Right? Negative 8 times 6 gives you negative 48. The denominator, we're looking for perfect cube factors, and there is a perfect cube factor of 27. So we can write that as the cube root of 27 times the cube root of 5. So the whole point of pulling out this perfect cube factor was to write it as an integer. Cube root of negative 8 is negative 2, and the cube root of 27 is 3. And then you still have these radicals, cube root of 6 over cube root of 5. And at this point you would probably just combine this, combine the two radicals and write it as the cube root of 6 over 5. Now, again, that would be if you were happy or content to have a radicand that was a non-integer. So what would you do if you didn't want to have a non-integer radicand? Well, at this stage, you could go and I'll rewrite this expression, negative 2 over 3 times the cube root of 6 over cube root of 5. You could, at this stage, rationalize the denominator. Now, rationalizing the denominator when you've got cube root of 5 is a little bit trickier than the example I showed you before, where you just had the square root of 3. Because if you multiply the square root of 3 by itself, you're squaring. So if you square the square root of something, you just have the radicand. However, if we multiply the cube root of 5 by the cube root of 5, we're not going to get 5, because we're really only squaring. We're multiplying something by itself, so we're really only squaring the cube root of 5. So what we really need to do is cube it. So we not only need to multiply it by the cube root of 5, we need to multiply it by the cube root of 5 another time. And that will give us an integer on the bottom. So on the top, we've got also the cube root of 5 and the cube root of 5. So what do we get here? The bottom becomes 3 times 5. All right, the cube root of 5 cubed is just 5. So 3 times 5, that gives you 15. The top is, the whole thing is negative, the top is 2 times, now since all the indices are the same, we can just go ahead and multiply the radicands. 6 times 5 is 30, times 5 again is 150. And so this would be the cube root of 150. And so that's what it would look like if you did not want to have a denominator that had a radical, or if you did not want to have a radicand that was a non-integer. So you could try plugging them into the calculator and verify that they are identical. They're just different ways of expressing it. All right. Let's take a look at some situations where we have variables. When is a radical defined? Now, what do we mean by this? Well, if you take the square root of x, you can't take the square root of a negative. There is no real number that when squared gives you a negative. And so the square root of x is only defined if x is non-negative. It's okay for x to be 0, because the square root of 0 is just 0. So for this we have to say this is only defined when x is greater than or equal to 0. Now let's think about something slightly different. What if we had the square root of x squared? Now, is there ever a case, is there ever a value of x that will give us problems here? If x is positive and you square it, it's positive. So you can take the square root of a positive number, no problem. If x is 0, you square it, you just get 0. No problem again. If x is negative and you square it, it becomes positive. And the square root of a positive number, again, no problem. So this is defined for all values of x. And we can do that by saying x is just a member of the real numbers. Remember that backwards 3 symbol is a Greek letter saying this is a member of. So x is a member of the real numbers. That basically just means we can plug any value we like into this. But what does this equal when we simplify it? Can we say that the square root of x squared is equal to x? And the short answer is no. We have to be a bit more careful here, because let's think of some examples. If we had the square root of 3 squared, well, that is just 3, because the square root of 3 squared is just 9. So the square root of 9 is 3. No problem, right? However, what if we had the square root of negative 4 squared? Well, as soon as you square negative 4, you get a positive. So square root of 16. But remember, when you use the radical sign, you're only defining it as the principal or positive square root. And so the square root of 16 is simply 4. But that's not what we started with. All right, we started with negative 4. So if our x value is negative 4, then here we're saying that the square root of negative 4 squared is actually the opposite sign of what we started with. And so to make sure that we always have a positive, we simply have to put absolute value bars around the x. So that guarantees that regardless of whether we're starting with a negative or positive x, it's going to be positive, and our equation is going to make sense here. The square root of something has to be positive, and so the square root of x squared is defined as being absolute value of x. We don't have to worry about this if we're taking a cube root. Cube root of x squared is just simply x. And we can also plug in any value we like here, because you're allowed to take the cube root of a negative. All right, a negative times a negative times a negative is negative, so the cube root of negative 8, for instance, is negative 2. And so it doesn't matter what x value we plug in here, and we also don't need the absolute value bars. In fact, we should not put the absolute value bars in, because if x is negative, then the cube root of a negative cubed is indeed negative. So you don't want to have the absolute value bars here. So when you do the problems in the book, it can be a little bit tricky, and I recommend doing every single problem and really spending your time figuring out exactly what is being asked and taking a look at the correct answers if yours are different, because it will be a little bit tricky at first when you're doing these problems. So let's just try a couple here. Let's say we have the square root of 20x cubed. So for starters, we're taking the square root of something, and you're not allowed to take the square root of a negative. Now, the coefficient there, 20, is already positive, so we don't have to worry about the 20. But the x squared has to be greater than or equal to 0. And x cubed has to be greater than or equal to 0. And it will be greater than or equal to 0 if x is greater than or equal to 0. So really that's our restriction there. We have to have this. X must be greater than or equal to 0. Otherwise this expression is just simply not defined. Now let's see how we simplify this expression. We can deal with the 20 and the x cubed separately. So the 20 we can write as square root 4 square root 5. The x cubed we can write as square root x squared square root x. So root 4, the reason we broke it apart as root 4 root 5 is because root 4 is an integer, 2. We don't do anything with the root 5. And then the square root of x squared. Now, the square root of x squared, I just told you a second ago, is absolute value of x. But if we've already defined x as only being positive or 0, then we don't need to write it in. Okay, if we didn't write the restriction here, x must be greater than or equal to 0, then we would want to write absolute value x here. But we really can't get away from writing x must be greater than or equal to 0 because of the fact that it's an x cubed in the radicand. If we allowed for the possibility of a negative x, then we would have a non-real answer. So really, we do not have to write the absolute value here because we know for sure that x is positive. So the square root of x squared is just x, and then we still have the root x that we don't really do anything with. And the last step here is just to combine the two radicals again. So you've got the 2 and the x, and then the root 5 times root x you would just write as root 5x. So both parts here are necessary, right? You have to have the restriction x must be greater than or equal to 0. Let's try one more, this time with a cube root. So cube root of 54 x to the 5th. You can, again, deal with, well, let's do the restriction first. When you have a cube root, it really doesn't matter what you plug in. So it doesn't matter whether the variable has an exponent that's even or odd, right? If it were even, then we know the radicand's always going to be positive. But if it's odd, then the radicand could be negative or positive, depending on whether x is negative or positive. But since it's a cube root, we don't really care. So any value of x is fine here. This expression is defined for any real number value of x. So let's break this apart. We'll take the cube root of 54 and look for perfect cube factors. 27 is a perfect cube, and 54 is 27 times 2. So we can write this as cube root 27 times cube root 2. And then when you're trying to simplify x to the 5th, it's actually pretty easy because you're just looking for exponents that are multiples of 3. So cube root of x cubed. And that leaves you with cube root of x squared. So cube root of 27 is 3. We've still got the cube root of 2. Cube root of x cubed is just x. And we've still got the cube root of x squared. So combine the two parts that are not with radical signs, 3x cubed. Sorry, just 3x. That 3 is an index, it's not an exponent. And then combine the two radicands, or radicals. Cube root of 2 and the cube root of x squared becomes the cube root of 2x squared. So, as I said, practice these, really check the answers. ask questions if you're not sure why your answer differs from the answer given in the book. These things are pretty tricky, especially the idea of whether or not you need the absolute value bars.